All right, today we're going to talk about, in general, what is thermodynamics and go over some basic definitions of a system, like a system, boundaries, what we're going to use to determine what our systems actually are. So, firstly, what is thermodynamics? Well, it includes air travel, space flight, building heating and cooling aspects of renewable energy and power generation. The first main step in a thermodynamic analysis is defining our system and figuring out its interactions with its surroundings, and then determining the physical laws and relationships to build our thermodynamics model. So, again, the first step in any thermodynamics problem is to define our system. Our system is basically whatever we want to study. That could be a quantity of matter contained within a closed, rigid walled tank, or something such as fluid in a pipeline. It can take a variety of shapes. A matter can be fixed, it can be changing. The shape of the matter can be fixed or can be changing. Everything that is external to the system is part of the surroundings. And what separates the systems from the surroundings is the boundary. So I'm going to draw a little bit of a picture here. So here I have my system. Everything in blue is my system. Everything around it in green. These are my surroundings. And then it's separated by our boundary. So there's two kinds of systems that we're going to study this semester. The first are a closed system, and the second are open systems or control volumes. So closed systems are defined as when a particular quantity of matter is under study, and for closed systems they always contain the same matter, so the matter inside the system is not changing, and there's no mass transfer that occurs across the boundary. However, energy transfer can occur. Across the boundary. It can occur by either heat or work. So I'm going to draw my picture again, where here I have my system. So this is a closed system. So my mass is constant. And here's my boundary this time. And again, everything out here are my surroundings. So how can energy or heat cross my boundary? Well, I can have a moving piston. So this is a piston, which is it results in moving boundary work because the boundary is moving. I can have heat transfer. I can have electric work. And I can also have shaft work. Now, a special type of system is a system that doesn't interact with the surroundings in any way, and that type of system is called an isolated system. What an isolated system looks like is if I draw my system and here's my boundary. Again, it's a closed system, so my mass is constant. All out here is my surroundings. Since it's an isolated system, no work or heat occurs across our boundary. So if those are closed systems, and the difference with open systems is that mass can cross the boundary. So a control volume or open system is our region within a boundary through which mass flows. So mass can cross the boundary. In addition to heat and work. So if I draw my system again, I can still have my piston up here. Put my boundary back in. I can still have my moving boundary work. But what's different is now over here, I can have mass flow. I can still have heat transfer. I can have more mass flow over here. I can still have electrical work. I can still have shaft work. So yeah, the difference between a closed and open system is for closed systems, mass cannot cross the boundary, whereas for open systems, mass can cross the boundary. So selecting your boundary in a thermodynamic problem is important, and it's generally done using two considerations. The first being what is known about the system. Particularly at its boundaries. And second, what are we trying to do? So for example, I have a picture here of a tank with an air compressor where the way the system boundary is shown, the system includes the compressor, the tank, and all the piping. This boundary can be selected if, for example, the input power is known and the objective is to determine how long the compressor can operate. Since mass can cross the boundary, this would be deemed as an open system. A control volume, if I had looked at just the compressor, could be chosen if I'm trying to figure out the conditions of the air entering and exiting the compressor, and if I know the properties of the air entering and exiting the compressor, I'm trying to find the power input. So the system that you choose will affect your overall analysis. So the last thing I'm going to go over is how we describe thermodynamic systems. There's two ways to do it. You have microscopic and macroscopic views. We're mostly concerned with the macroscopic view in this class. So the macroscopic approach is concerned with the overall system behavior. It's called classical thermodynamics. It does not model the system at the molecular, atomic, or subatomic level. So important aspects of the system are, like, how the system behaves are evaluated from observations. Of our overall system. The other approach is microscopic. It's called statistical thermodynamics. It's directly concerned with the structure of a matter. And you characterize the average behavior of our particles making up the system. And then you relate that information to our macroscopic observations. In our next lecture, we're going to go over what is a property, what's a state, and what is a process.